Welcome to Chapter 12, Module 3. In this module, we'll discuss constrained resources and split-off considerations. You all ready, Sketch?
I think I have a constrained source. Sleep.
That's a sure sign it's time to start. Let's start with how to determine the most profit when we have a constrained resource. First up, let's define what we mean by a constraint.
A constraint is a limited resource that restricts the company's ability to meet demand, like a shortage of raw material.
Or it could be a process that has a limited output. If the constraint is a machine or a process, then we call that a bottleneck. Some rules of constrained resource problems are: first, fixed costs are usually unaffected in these situations, since they happen whether the constrained resource is a factor or not. So we look for the product mix that maximizes the company's total contribution margin to maximize profits.
To maximize profits, we wouldn't necessarily make the products with the highest unit contribution margins.
Instead, we focus on the products or the orders that provide the highest contribution margin in relation to the constraining resource. Let's look at an example. Assume that Ensign Company produces two products that have unit contribution margins of $24 and $15 respectively. If we didn't have a constraining resource, we would maximize production of the product with the $24 unit contribution margin in order to maximize profits.
Product number 1 requires 1 minute of time on machine A1. Product number 2 requires 1/2 of a minute.
Just a quick check on something. How many units of product 1 can the company make in 1 minute?
Unless that's a trick question, I'd say 1.
That's right. And how many units of product 2 can the company make in 1 minute?
Oh, I think I see where you're heading. They can make 2 units of product 2 in 1 minute.
In addition, let's assume that machine A1 is a constraint, and there's an excess capacity on all other machines. Machine A1 has a capacity of 2,400 minutes per week, which is less than we need to meet the demand on both products together.
So the question is, which product should Ensign focus on to maximize company profits?
If machine A1 is a constrained resource, what generates more profit for the company? Using 1 minute of it to produce product 1 or using 1 minute to process product 2?
It would have to be product 2. With that 1 minute of machine A1, we could make 1 unit of product 1 with a contribution margin of $24. Or 2 units of product 2 with a contribution margin of $15 per unit. So 1 minute gives us $24 with product 1 and $30 with product 2.
To solve this type of problem, we calculate the contribution margin per unit of the constrained resource. Whichever is higher should be the product that's produced first to maximize our profits.
In this case, we divide the $24 contribution margin by 1 minute and the $15 contribution margin by 1/2 of a minute, or 0.5, for a contribution margin per minute of $24 and $30 respectively.
Therefore, we should emphasize product 2 because it has a contribution margin of $30 per minute of the constrained resource, which is higher than the $24 per minute for product 1. Ensign can maximize its contribution margin by first producing product 2 to meet consumer demand and then using any remaining capacity to produce product 1. We start off by fully satisfying the weekly demand of 2,200 units for product 2, since that had the highest contribution margin per constraint.
This would consume 1,100 minutes of available capacity on machine A1.
Then we figure out how many minutes are left by subtracting the time to make product 2 from the total available minutes for the constrained resource.
This gives us 1,300 minutes left over that we can use to make product 1.
Since each unit of product 1 requires 1 minute of A1 machine time, Ensign could produce 1,300 units of product 1 with its remaining capacity.
So to maximize profits, we should make 2,200 units of product 2 and 1,300 units of product 1.
Multiply our contribution margins and add them together to give us a total maximum contribution margin of $64,200 with this constrained resource. Next up, let's determine the value of obtaining more of the constrained resource. If increasing the capacity of the constrained resource can lead to increased production and sales, how much should we be willing to pay for that additional resource? Because the additional machine time would be used to make more units of product 1, Ensign should be willing to pay up to $24 per minute more. This amount equals the contribution margin per minute of the machine time that would be earned producing more units of product 1.
If they pay any more than that, they would start to lose money.
Managers try to increase the capacity of a bottleneck in a number of ways, such as working overtime on the bottleneck. An example would be running it on a second shift.
They could subcontract some of the processing that would be done at the bottleneck. Find a vendor that can do the overflow work for you.
Maybe by investing in additional machines at the bottleneck, or shifting workers from non-bottleneck processes over to the bottleneck.
Managers would focus on process improvement around the bottleneck. Any improvement that doesn't increase the bottleneck is considered a waste.
And then by reducing defective units that are processed through the bottleneck, which frees up more space for units that are good quality. All these things would help open up the bottleneck, which would increase production output. Next up, let's discuss joint products. It's not uncommon for companies to produce several end products from a single raw material input. If we have 2 or more products from a common input, they're called joint products.
The split-off point is a point in the manufacturing process at which the joint products can be recognized as separate products.
Let's look at an example. In the petroleum refining industry, a large number of products are extracted from crude oil, including things like gasoline, jet fuel, home heating oil, and lubricants. We have a single raw material or input of crude oil, and at various times throughout the manufacturing process, we reach split-off points for the various end products.
So a company would want to know which end product is most profitable, so they could emphasize that production over others.
The term joint cost is used to describe costs incurred up to the split-off point. Joint costs are common costs incurred to simultaneously produce a variety of end products. These joint costs are not relevant in determining which end products to make because they happen for all the products, so they're not a differential cost. We traditionally allocate joint costs among different products at the split-off point. One approach would be to allocate joint costs according to the relative sales value of the end products.
Although allocation is needed for some purposes, such as balance sheet inventory valuation, allocations of this kind are very dangerous for decision making. They can lead to misleading data that causes bad decisions.
As we mentioned, joint costs are irrelevant in decisions regarding what to do with a product from the split-off point forward. Because of this, we don't allocate them to end products for decision-making purposes.
With respect to sell or process further decisions, it is profitable to continue processing a joint product after the split-off point, so long as the incremental revenue from such processing exceeds the incremental processing cost incurred after the split-off point.
Let's look at an example. Sawmill Inc. cuts logs, which creates lumber and sawdust. They can sell both as is at the split-off point, or process both products further to sell as completed products.
So Sawmill would want to know which leads to the higher profits, to sell the products at the split-off or further refine one or both of them.
We're given the following data to help us figure this out. Sales values at split-off is $140 for lumber and $40 for sawdust.
If they further refine the products, the sales value becomes $270 and $50 for lumber and sawdust respectively. The allocated joint production costs are $176 and $24 respectively, and the cost to further refine is $50 and $20.
Sawmill wants to know if they should further refine either the lumber or the sawdust, or maybe both. To solve this type of problem, we look at the incremental increase in refining costs after split-off compared to the incremental increase in revenue. As you might guess, the allocated joint production costs are not relevant, since they happen whether we further refine or not.
The sales value after further processing of the lumber is $270, compared to the sales price at split-off of $140, which gives us an incremental revenue of $130. The cost of further processing is $50, so there is a profit of $80 per log to further process the lumber.
The sawdust has a sales value after further processing of $50, compared to the sales price at split-off of $40, giving us an incremental revenue of $10. The cost to further process the sawdust is $20 per log, which leads to a $10 loss to further process the sawdust. So in conclusion, the lumber should be processed further and the sawdust should be sold at split-off. Let's stop here for Chapter 12, Module 3. See you next time.